So let's start the second part. So as you can see on the bottom of the slide, after some time, one begins to understand molecular recognition and to practice pre-organization, which means making locks for keys or keys for locks. That's pre-organization, pre-organizing your entity so that it fits or it binds selectively. It's another one. When you understand that better, you can ask you the question, can we use it to induce self-organization? In other words, using molecular recognition to direct the way in which objects assemble in a designed fashion. You want this to be spontaneous, but you want to direct it. You want to have a control over it by the way in which you shape your entities, by the type of interactions you put in, the recognition patterns. So you want to control it by the molecular information and the way you process it. Now, I mentioned already that most of the systems presently studied are equilibrium systems, but non-equilibrium self-organization is, of course, very important because, after all, complex systems are non-equilibrium systems, like living systems. And I indicated that, in fact, a major area where non-equilibrium is even the core of it is transport processes. So about self-assembly, all living organisms are self-assembled. They make themselves spontaneously. But they are too complicated. A simple case is tobacco mosaic virus. I could have taken another virus. I will tell you a story about another one. So tobacco mosaic virus, which is what? It's a supramolecular entity, aggregate, of 2,130 bricks, protein subunits, one RNA, the genome of the virus. If you mix together the genome and these bricks, which that's a crystal structure, that's a bit less detailed, and that is completely schematic, they just get together. They get together like a piece of pie. They get together and then they go around. They have a shape somewhat conical. So obviously, if something is conical, they must go around. It's quite obvious, nothing very complicated. It's pure geometry. And you get finally this entity here. Now when you look at this, you say this is magic. But it is not magic, because all the features in these compounds we know, we can explain. It's organic chemistry, it is physical chemistry, it is kinetics, it's thermodynamics, but there's nothing magic. And in fact, I should have brought, maybe I have it here, wait a minute. Oh no, on my computer. Wait a minute. I thought I had put it on. I did not. Okay. So then let me just tell you. There is a video you can easily find on Google. I think you can find it on Google, on YouTube probably, where people did the following. These were young people from California somewhere. There are some viruses are spherical, okay? And one knows exactly how many proteins make up the sphere. So they took plastic, they made a sort of a concave type of entity, which had a shape, little bit like the protein making the proteins of the virus. And they put on this little piece little magnets at the positions where the proteins interact. Okay? So they took a beaker, they put 20 of those things in, or how many, and they shake the beaker. And after a minute, you have a sphere. If you look at it, that's not possible. You have these things, you just shake. So you see it building up, breaking again, building up, and the end you have a sphere. They get one step further. They took plastics, red color, and a little bit different size, green color. Then they built a machine for shaking because it takes longer. So you have a beaker with red parts, green parts, and it shakes. It takes longer, and about after 5 minutes, you have a green sphere and a red sphere. It's incredible. But it also means it's so simple. It's just driving, the organization is driving the system to get more and more stable entity. In this case, it's the magnets which make the stability. So it's worth seeing that movie, because it's sort of, when you look at it, you say, after all, organization is part of the whole thing. It wants to organize. I mentioned Christian de Duve earlier. In fact, he has written a book called Vital Dust, Poussière de Vie for the French people. And the subtitle is Life as a Cosmic Imperative. In other words, that is also what I wanted to put with self-organization. For me, self-organization is a cosmic imperative. In our universe, things self-organize. And life is not an accident. Life is everywhere. Everywhere. Everywhere where it's possible. Okay, that can be discussed, I agree, because we cannot go there and check if it is right. Anyway, so this thing looks like, as I said, a program. Of course, the little magnets are also somewhat programmed, the example I gave. So the program is molecular, with information in the components, and it operates in a supramolecular fashion by recognition between the pieces. And like in a computer, you enter information, you let it run, the virus builds up, and at the end you have the viral particle. Okay, the types of self-organized objects you can think of, there are two big categories. Some are discrete objects, like a virus particle. A virus is a discrete object. It is finished, it has a given number of bricks, components, and it has a given structure, a given shape, and all that. That's a discrete object. Then you have also extended assemblies. These extended assemblies are not defined usually in terms of size, or not well defined. Like supramolecular chains, we will come to that for polymers. Two-dimensional layers, films, and so on. A film has no size. I mean, it depends on how much big you want to make it. And three-dimensional solids, crystal engineering, these are three-dimensional objects which are extended assemblies. Now, I think I'm going to drop the hydrogen bonding to not be too long. I drop this. And just to indicate that you can also, by molecular recognition, it is hydrogen bonding, but I want to insist on the fact by using molecular recognition, you can also control the fate of large things. And one large thing of interest is, of course, a cell, how do cells fuse. Now, the fusion of living cells, or cells in organisms, is a complicated process with many proteins which come into play. But I can show that you can realize that by a rather simple approach also. Suppose you make a vesicle with phosphatidylcholine or something like that, and you make a recognition group, a lipophilic recognition group, which has a recognition group, a hydrophilic spacer, because you need something a little bit watery, get into water, and a lipophilic tail. And you have two recognition groups, the red and green, complementary ones. The red one can be, for instance, this, barbiturate, and the green one, triamino pyrimidine. And these are complementary. NH, this was hydrogen bonds at the interface. So these two complementary recognition groups, red and green, you can put them into vesicles and then ask the question, what are the vesicles going to do? What they can do, you mix them, they can first get together, attach, and then exchange their components, and then they become neutral, and they don't attach. But they could perhaps also fuse slowly by opening their membranes, thanks to this interaction. That's a possibility in principle for drug delivery. But between the word and the realization, there's a long way. So this is just an example to show you. This is one type of the vesicle. Which one I don't remember. Is it the tap or the bar? Anyway, it's one. They are the same. You make these vesicles. Some have tap, and another batch has bar. Then you mix them. After 10 minutes, you see these aggregations forming, shown here. And if you wait much longer, you get very big fusion. So you get these vesicles fused together. They don't fuse if you don't have complementary. I could have shown that also with interaction of metal ions with binding sites and so on. I didn't want to get too much into it, but I wanted just to show that indeed with rather small recognition groups, you can induce fusion of these large vesicles. Yeah, this is the one. Yeah. Oh, I have it. I thought I had taken it away. Okay. So you can also do that in the following way. You can use a bipyridine or any kind of metal ion binding entity. You put tails on it, again with the same principle, a hydrophilic spacer and a hydrophobic chain. And now the vesicles have this kind of things which look out, but they don't talk to each other. Then you can add a metal ion which will bind them together. And here you can see quite nicely the fusion. So these are these bipyridine containing vesicles. We call them metallosomes, liposomes, metallosomes, or recosomes for the recognition ones. And you can see these were giant vesicles, so you can observe them by microscopy. And you see here, these two are together. You follow them in time, and they fuse. At the end, you have this vesicle. It's just an observation of the progressive fusion of vesicles and mixing their contents. That's also an interesting process because it's a way in which you can compartmentalize two objects. That's something we should have done. We haven't done it, but I think somebody should do it. To take one which has, for instance, let's say luciferase, and the other one has luciferin. And when they fuse, they will emit light. So that would be a way to show that contents interact. That's some work to do of interest. 2, oh, good. Okay, now we said let's look at self-organization. And since I have dropped the hydrogen bonding things, I will look at something which is developed quite a lot in Strasbourg, and the Hamburger groups has worked on it, where we can try to build up architectures which contain metal ions. They have this sort of cumbersome name, metallo-supramolecular, but it means what is correct, that the architecture resulting from this building up is an architecture which is built up of bricks, which are ligand molecules, and of cement, which are the metal ions. Now, if you want to use again this language of information, the metal ions will process, they read and process the structure information which are in the ligands, and you have a supramolecular coordination algorithm. And this is very powerful and can make you design very complicated objects. And of course, Makoto Fujitada's group have done fantastic contributions to using metal ions in building up complex structures. The metal ions are quite interesting, much more. In some respects, biology uses hydrogen bonding because hydrogen bonding has just the right energy to be good for life, because you don't want to be too strong. You have to be in the temperature and pressure conditions of our Earth. You have to have interactions which are not too strong. DNA has 2-3 hydrogen bonds. It cannot probably not work with 4-5 because it would be too stable. So 2-3 is just what you need. So, however, metal ions are much more interesting in absolute terms than hydrogen bonds. They provide a set of coordination geometries. Hydrogen bonds are rather dull. They are this. Whereas metal ions have many more possibilities. A range of binding strength, which is enormous, from binding a potassium, let's say 5 kilocals, 6, maybe 10 kilocals, to ruthenium, 50, 60 kilocals, an enormous kinetic strength, range, and kinetics also. Properties, you can oxidize them or reduce them. You can photochemically activate. You can do reactions on metal ions. You can switch them, redox, plus you can take electrons away, put electrons in. And they may also be addressable. That means maybe you can talk to them, putting electrons at a given place. We'll see one example of that. So let me just show you about what we can call the helicate world. This is not the DNA, it's not the RNA world, it's the helicate world. What is it? It is trying to make helical structures in a designed fashion by encoding exactly your strands so as to generate given structures and to play with it. So, first of all, let's see, now at the beginning we just stick with sort of geometry. If you have a unit with two binding sites, bidentate, and you connect it through a tetrahedral organizing site. I replace it by a square because it's more easy to picture than a tetrahedron. So, tetrahedron is 4 points in space. 2 by 2 points in two perpendicular planes, this and this, that's a tetrahedron. So these two entities, if they bind in a tetrahedron to a tetrahedron, they will do this, okay? One green thing will be perpendicular to the other green thing. The same is correct for octahedral. An octahedron is 2 times 3 points in two perpendicular planes. So if you use 3 tridentate with octahedral, represented by a hexagon, you get again this perpendicular. Between the two, trigonal bipyramidal is 2 plus 3, and you get the same. So in principle, that is general, because we had been working a lot with bipyridines and so on. For us, bipyridine and terpyridine were the bidentates and tridentates. But others have been developed by Marcus Albrecht, for instance, and other people, where other metals have been used and so on. Now, for simplicity, we will call bipyridine B and terpyridine T. You will see why. So that is another representation of the same thing. Bidentate tetrahedral 4. Coordination number 4, these are perpendicular. Tridentate octahedral, coordination 6, these are perpendicular. Trigonal bipyramidal 2 and 3, they are perpendicular. What is interesting is that there are, so to say, two bases, B and T. But there are 3 connections, BB, TT, or BT. And the pairing is perpendicular, not flat, like in DNA. So you have another ball game where you can play with it and use these possibilities. You have only 2 bases, but you have 3 ways to put them together. So if you take like an oligonucleotide, a trinucleotide, you would have 3 nucleotides in a row. You have BBB, 3 Bs in a row. If you treat this with tetrahedral coordination, what will happen? This guy will bind here, and if it cannot bind back, that's of course a problem, the question. Thermodynamics control it. Then it will take a second strand, and obviously this unit from one strand and this from the other, they will be like that. So if 2 are like that, the other ones will go like that. So the result of it is that you generate out of a BBB strand a double helix where the centers here are tetrahedrally coordinated. This is old stuff again, but I think it was the beginning at that time where this was synthesized. That's like a trinucleotide, a BBB, tris-bipyridine, copper 1, and they wrap around each other to generate this double helix. You don't see the coppers, they are here. The reason why it's copper 1 with bipyridine, for those number of people in this room know what that means, but others don't. Bipyridine with copper 1 requires tetrahedral coordination, so it does this, okay? We'll see copper 2 what it does in a moment. So you can do that with longer chains, 2, 3, 4, 5, and you get this dihelicate to pentahelicate where things wrap around. And these have been very well identified, and everything is in order. I just show those because I need them a bit later. TTT, same game. I don't want to insist, but from what I told you, TTT, octahedral, each side is perpendicular like this. It makes double helix, which is homotopic, homostranded, the same sides and the same strands. Here is the crystal structure. Here you see the ions that are sitting here with iron. This is iron, with iron centers. It also works with cobalt, with nickel, manganese, I don't remember. I think zinc works also. So this was simple, BBB, TTT. Now we use BBB and TTT. Now 2 and 3 is 5. So what do you want to use? You need something which wants pentacoordination, coordination 5. And then you should get this. What is it? Quite interesting. There is probably just one cation in the whole periodic table which will take together a bipyridine and terpyridine that is copper 2. Luckily, it's also copper. So copper 1, copper 2, you see there's also possibility to interconvert. And indeed, when you take this TTT strand with this BBB, you get the mixed heterostranded homotopic double helix crystal structure shown here. And you can continue playing. You know, now people make oligonucleotides. One can make oligobipyridines. You play, you put sequences. You take BTB. Now you treat with 2 squares, about 2 tetrahedral, 1 octahedron. You get tetrahedral, octahedral, tetrahedral. Okay. You take TBT. Of course, now you reverse the thing. It's just playing around. It's just a game here. 2 octahedral, 1 tetrahedral. You get that. And again, this works. There's just one case with BTB, copper 1, iron 2, copper 1, crystal structure of that. That was done by Virginia Smith. Unfortunately, it published very little of it, no structure, but there's at least one paper out. Now, take BTB and TBT. This is 5, 5, 5 on different strands. You treat with copper 2, and you get this thing, which is heterostranded. And the interesting thing one should note is that pentacoordination is a translation, so to say. It translates a 2 into a 3. So this is sort of interesting because if you can make these bonds dynamic, which is something one should try, you can select and translate one chain into its complementary chain through this interaction. So the last thing I want to show you is this. I'm going a bit fast here because it's just playing with these entities, but I think it's interesting to see how you can do it. But there's something more, maybe a step further in terms of what comes out of it is the following. This you have already seen. I just showed that. Now, let's do a very simple change. BTB, you just shift that over, you exchange those two, and make BBT. Looks trivial. But something interesting happens. You take this molecule BBT, you react it with 2 tetrahedra, 1 octahedron. You get tetrahedron, tetra, and hexacoordinate octahedron. Then you react it with pentacoordination and tetrahedron. You get penta, tetra, penta. What is interesting here is the following. In the first case, the 2 strands are parallel. You have 2 BBT, BBT on each strand. In this case, you have BBT, and here you have TTB that turned around. In other words, depending on what you do with this strand, you get a different product. So the molecular information in here is not enough to determine what you get out. What determines it is also how you read that information. So you have the case of the same molecular information. If you process it through different interaction algorithms, you have 2 different outputs. One program, in this case 2, but in principle, there might be several. That is also something interesting in terms of the relationship with biology. In biology, one code, one protein. Whereas in this at least indicates that you can have molecular information, but the way you process it can give you something different. In other words, the information is, so to say, degenerate, and the interaction lifts the degeneracy. Okay, you can also make triple helices. Of course, octahedron is 3 times, hexacoordination is 3 times 2. So you make strands with bipyridines, but now you take octahedral metal ions, and then they can wrap around here and make an octahedron, an octahedron, an octahedron, and you get a triple helix. Here's other properties of interest, but I haven't time to get into it. Finally, in the last of the silicates, and they will come up again a bit later for another totally different reason, it happens that you can also condense this BBB with octahedral coordination in a way which gives a circular helicate, a circular double helicate. And if you follow me, you can see that this is one molecule here, this, so that the center is bound to one of the octahedral coordinated midlines, and the ends of 2 other molecules complete that. So each center is bound to each octahedral midline is bound to the center of one strand and to the ends of 2 other strands. And if you do that, you can go around like that. So first thing, does it work? That's the strand, iron chloride. Okay, it's a bit brutal, because, you know, that is why biology, I told you biology uses hydrogen bonds. Because if you want to do things like that, you have to heat. Otherwise, it doesn't work. And if you use metals which are ruthenium or iridium, then you can heat it for a long time to get it at the end, to get a thermodynamic equilibrium. Now, of course, it works also less than 170 in glycol. But if you want to finish your PhD in a reasonable time span, you better heat it. So this is what you get, a pentagon, 5 irons, fine, 10 plus, and in the middle, a chloride. This is the crystal structure with the chloride. Now this is very important. This chloride is very difficult to get out. Why? Easy to understand. 10 plus, 1 minus, very strong electrostatic interaction. So the chloride is it fits very nicely. You see, it fits exactly in the hole. And this indicates that this structure must be very stable. There's something special to it. If you take not chloride, but tetrafluoroborate or sulfate, iron sulfate, you get a 6-membered entity. We don't have the crystal structure of that, but we are sure it's that one for all the other spectroscopic measurements. Now, you may say, okay, it's nice to talk about all this information stuff, but you showed us that a given strand, this linear one, with iron or nickel gives a triple helix. And now you just showed us that it makes a circular helicate. What's going on? We don't understand what you're doing, because, okay, it gives one, gives the other one. Why is it like that? And this was a little bit, this was also quite interesting in terms of the way one does work. Once Bernard Hasenkopf, who did that work, he had at the beginning, he had looked at his compounds immediately after preparing them. He got triple helices. And then one day, I don't know, maybe it was a weekend or something, he waited and he got something else. He got the circular. So what happens is that the first step is the formation of the triple helix. And when you wait long, you get this, which means that you have perhaps a bifurcated mechanism, or the kinetic product can also transform into the final one, into the thermodynamic product. We don't know exactly what the mechanism is, but what we know is that it's a sequential mechanism. We can isolate this. That's in some ways the advantage of metal ions. Things are slow. So when things happen, you can isolate sometimes the intermediates. And here, it happens that the first step is the triple helix. You can isolate it. If you heat it again, then you get this. So you have a kinetic product and a thermodynamic product. And of course, in most of the assemblies we are doing, there are always kinetic products around, but they are moderately fast, and often you don't look at it. And so you get, at the end, the thermodynamic product. But it's interesting, because the kinetic product is, of course, something which is not in equilibrium, not in thermodynamic equilibrium. The stable one is this guy. Another type of supramolecular entities we were interested in, and here I mention ours, but of course there are so many interesting ones around, including the ones coming from Japanese group. I just tell you stories about the ones we have been studying. Can you make arrangements like that, which look like sort of electronics piece? If we were not talking about chemistry, you would say, okay, that looks like sort of electronic stuff, where you have grids with, let's say, some conductors or some wires or something, perpendicular to each other, held together by something gluing them together at the point where they cross. Now, if these are the starting materials, if these slots here are well constructed correctly, if you treat it with the right assembler, the assembler midline, then you should get this 2x2 grid, 3x3, 4x4. These are the molecules one can use, where you have subunits with 3 nitrogens, tridentate, 1, 2, 3, 1, 2, 3. And if you use the principles I have told you about earlier, obviously, if you treat that with octahedral coordination, these 3 and 3, they do this. And of course, once you have started somewhere, it closes up. So you take this, this, and this, and you get 2x2, 3x3, 4x4 grids. What they have is that they are now, compared to the single site, the one with only one metal, they are multi-ligand, multi-nuclear, multi-metallic. That means you can have different metals. I haven't time to get into that, but you can put different metals on different positions. So what are they good for? Obviously, the simple one is this one. So this was most studied by far. The other groups have studied also very nice manganese type of compounds have been made and which have been described in the literature. So 2 slots, 4 cations, 4 ions, and you get 2x2 grid. That's the assembly, and that's the crystal structures. That should show you that it's correct. What do they show as properties? The properties they have, because they are multi-ligand, multi-nuclear, multi-metallic, they have now multiple redox states. Multiple redox states, the 2x2 grid, for instance, I will not show you the Celtic voltammograms, which are totally reversible. You can go up to 12 redox states, which are reversible. I think the Bologna group had also one, a very high one with many electrons. And we had a sort of talking together who has the largest number of redox states. So this has 12 redox states, reversible redox states, with cobalt. So I should add that the electrons, they don't go onto the cobalt, they go into the ligands. Maybe I should have put that slide in, but I wanted to show you the magnetic properties. What happened is, when Esther Browning, she was a PhD student, I gave her this thing to do. We had made grids and told her, look, why don't you use iron to assemble it? I thought it was a simple case, just to learn the job. So she did it, and she came around and showed me a spectrum like this. Look, wait a minute, 80 ppm minus 20 cannot be correct, because it's known that bis terpi iron is diamagnetic. This is high speed, this has magnetism. So I said, look, let's see what happens when you heat and cool. When you heat, you get this nice spread spectrum. When you cool, the bands broaden and they reassemble in the low spin, in the non-magnetic region. So in fact, what happens is that these 4 iron centers undergo a spin transition from high spin at high temperature, low spin at low temperature, and the spectrum, the NMR spectrum, is a very nice diagnostic way. It's lucky that it falls just in that region, diagnostic way to show that. Then because of this iron magnetism, Philipp Güttlich in Mainz is a great specialist of iron magnetism, so we collaborated on that. They analyzed that system in more detail, and they came out with the fact that not only is this change temperature dependent, but you can also press on it, pressure dependent, and you can induce transitions, light transitions between the spin state. In fact, light transition, this is one of the things which have been discovered by Philipp Güttlich in iron complexes. And in fact, the reason why pressure acts is that high spin and low spin iron don't have the same size. So if you press on it, you favor one or the other. And with Kari Risanen, he did some crystal structures at room temperature at -100, and you can exactly see which are the centers which are high spin and which are the centers which are low spin. So it's a rather unusual type of substance where you have multiple spin states. Of course, altogether there are 5 levels. Everything low spin, everything high spin, and these 3 between. These are Mössbauer spectra, which show you the low spin and the high spin. And you have 3 levels which have been studied, this one, and you have 3 triggers: temperature, pressure, and light. Whether it has any use, I don't know, but at least it shows that multiple sites bring properties which, of course, single sites don't have. Now, these are bulk properties. What about being able to talk to those things? You can deposit, this is the Kriegsway structure of the cobalt complex, on graphite, and then look at it by STM, and look especially at the current. First of all, you can image, and you see here 4 dots, which correspond to the 4 cobalts. And when you then look at the currents passing through the tip, you see that there are 4 positions where the current increases strongly. This is a calculation by somebody Korthus in Stuttgart. When you pass over the cobalt, you have an increase in current. So that's really, so to say, talking to the ions. You just see, you can, when you pass over, feel, measure an increase in current. Now we have grids where we have rutheniums on one diagonal and irons on the other. But should probably look at it also and to see if the currents are different, because then you can, of course, have a pattern. It wasn't done. Now the largest one we made is this one with 4 centers, 1, 2, 3, 4. You treat with lead 2, and you get an assembly in 1 step of this unit, which has 16 leads organized in a 4x4 type of structure. This again can be spectroscopically attributed. You could even say addressed, although it's not in the radio frequency range, as you will see in a moment. There are 4 leads which are identical in the corners. There are 8 which are identical in the edges, and there are 4 identical in the middle. Now lead has a nuclear spin, so you can do NMR on lead. So you should have 2, 4, 2. Sorry, 4, 8, 4. That means 1, 2, 1. 1, 2, 1. 4, 8, 4. That's exactly what you have. 1, 2, 1. The green ones is this signal. This is an old spectrum. You see that immediately. That's not a recent spectrum. But it works. And this was also a proof that we had the right structure, because it took a long time to get the crystal structure of that. It wasn't so well organized. It took people at the synchrotron in Grenoble a long time to get the structure. We have the crystal structure, so everything is fine. But this already was an indication that the structure must be correct. Now, one can insist on the fact, but I guess all the people working in this area realize that whereas present-day nanoscience and nanotechnology counts on the ability to fabricate and to manipulate on a nanometric scale, which obviously is a very powerful methodology, since we know that we got all these fantastic machines which work so well. Nevertheless, there may be another way of approaching the topic, which is to let the system make itself. Now we are far from that, but in principle, there is no principal objection to the fact that you make a piece, you design your system in such a way that when something assembles, it prepares the stage for the next one. I have not added slides. We have done that with Mario Ruben, where you can make a grid, and when the grid is formed, you can connect these grids in a second step. Now, these are only 2 steps. Doesn't go very far, but it's just preparing the stage whereby you will be able, hopefully at some stage, to assemble something, make a first step, then a second step, and a third step, and so on. Of course, it's a bit dreaming, but on the same hand, it is theoretically possible. So that's the way from fabrication to self-fabrication, which is the ultimate. Let the thing make itself, but of course you have to understand how things operate. To show that, and to show a case which is more complicated, let's analyze the following. I told you that this type of entity wants to make a double helix. This type of entity wants to make a grid. Now you synthesize a molecule. This was done by Daniel Funeriu. This helix, grid, helix. So you have, like in a program, 2 subroutines. One subroutine is a helix forming, double helix forming. The other subroutine is a grid form. Now what is this molecule going to do? Sort of frustrated thing, doesn't know really. What can one do? First, you take this and you now use, coming back to what we said about double helices earlier, 4 octahedral, 8 tetrahedral. Now you realize immediately what will happen. 4, that is this, 2 by 2 grid. But now if it forms a 2 by 2 grid, what are the other guys going to do? They want to make double helices, and they make them in this way. So you consider that this is a linear combination of the 2 programs, whereby what forms helices, what wants to form a helix forms a helix, what wants to form a grid forms a grid, and generates this. But that's not all. You can now say, okay, let's try with 5 coordination. How do you make 5 with this? Obviously, by taking one of the 2 and connecting it in some way with one of the 3. So that's a strange thing, because it needs this to go back over there and have entangled entities. And indeed, that's what you get. So if you see, this is one of those molecules where you go this way. That's one. This is one, so that's another one here. So they are very highly entangled, as you can see. And they make this where you have a sort of a crossover of the 2 programs. The grid forming and the helix forming go together. Now, how do we know? Of course, this nobody believes you if you don't have a crystal structure. Luckily, that thing crystallized. Come on. And here it is. So thanks to that, we are convinced that we have it. Otherwise, you sort of would think, how it is possible? Now, this illustrates once again, this we don't have the crystal structure, but we are sure that it is this molecule on the basis of all the other properties. But of course, the most interesting one is this one. Now, this indicates how this connection between ligands and metal ions, how powerful this is. And of course, this has been shown in many very complicated cases. For instance, in Makoto Fujita's group, and also in Stoddard's group, for instance, when they make these Borromean rings in one step. Look, you look at it, you say, 10 years ago, these guys are crazy. Put them in an asylum, they are crazy. And you just mix the right stuff, and they're even trivial molecules. Trivial components, trivial metal ions, you let it go, and you get. And I guess we are just at the beginning of the possibility to make very complicated structures by this way. Also in the solid state, like Weiss-Hosseini's group, they do, to organize things, and the powerful organization. This is something we will better and better understand, and will give us a lot of openings into very complicated structures. Of course, at the beginning you look at structures, but then you look at properties, and as time goes, you go more into functions. Now, we change. Up to now, I told you about that we want to design systems, okay? We want to design objects, systems where the objects are designed in such a way that when they get together, either by themselves or with the help of a midline to bring them together, they generate something you want to control. You design, you program, and there's an enormous field which has shown how powerful it can be. And as I said a moment ago, we are just at the beginning. But then comes another thought, which is to say, why not let the system choose what it needs? Self-organize, but by choosing the pieces it needs from a diversity of pieces. There can be a selection, hopefully, where the self-organization principle itself leads to the fact that out of diversity of building blocks, you can select the right ones. But you need dynamics. That means that you need to be able to have a searching procedure, because the first thing these things happen, any reaction happens by collision. Molecules collide and react. Assembly, they collide and then react, or assemble. So if they stick together too strongly, you are finished. You get a mixture of many different things. So you need things which sort of touch and sort of feel out. And if they don't do the right thing, the right meaning not thermodynamically the best one, the most stable one, they can detach and assemble in a different way until they reach the thermodynamic minimum. I repeat that we are always working at equilibrium conditions, in thermodynamic controlled conditions. This opens the way towards adaptation, because if the system can select, if you perturb it, it will perhaps select differently. That means it will adapt to the fact that it has been perturbed. And this opens to adaptive chemistry. So, where did this come from? In fact, initially, there were two observations, in fact, three observations, which were very important and which sort of opened for me the way to go there. This was already a long time ago, in 1993. I told you earlier that we had synthesized these four strands. And separately, they give double helices with 2, 3, 4, 5 centers. Then you do something which an organic chemist hates to do. You mix them. Usually, you chromatograph, you get pure compounds. You're happy with pure compounds. But yeah, you mix them. But then you can ask a question which you cannot ask with pure compounds. We do now the same reaction. What's going to happen? We treat that with copper-1. Will you get a horrible mixture of all possible combinations, or will the system self-sort, self-recognize, so as to form the correct double helices? That's what happens. The mixture with copper-1 generates a mixture of the correct assemblies. Now this is quite interesting. It means that the system in some way finds its way. Of course, it means that that is a thermodynamically most stable state. But it nevertheless indicates that if the system is designed the right way, you end up in the mixture to generate what you would have had with the separated entities. So you get the correct pairing of the strands. Now you can do the same, a bit more complicated. The strand which gives a double helicate with 3 centers, the strand which gives a triple helicate, this one, with triple helicate with octahedral centers, nickel. You mix the things again, and you let it run. What you get? The correct double helix and the correct triple helix. Again, here there's a double choosing. They have to choose the right ligand and the right metal ion, because this is a combination of both, so they search out. I'm pretty sure that nickel also binds to that guy for some time, but it doesn't stay there. And so you get the correct, and the difference is not very big. Now, I must admit, we should have calculated that and to see where are the fine details. But let me just point out, what's the difference between this strand and this strand? Just the oxygen. The oxygen in the middle between here and here. There's no oxygen here, there's an oxygen here. And that is enough to make it this prefer nickel and this to prefer copper, and to get this out. So that was indicating something very interesting, that out of a mixture you can do a separation of the objects, you can get the same objects, you can get the correct objects, but this depends, of course, on the fact that there are dynamics, that the system can explore the energy structure hypersurface. It is then meaning that you need dynamic coordination sites, and it's a sort of a dynamic set which finds the way to generate these objects. Now the first remark one can make is the following. Pure compounds are what we are always looking for. But the important thing may be, and I'm sure, is not having pure compounds, but having instructed components. In other words, I don't advocate to make dirty compounds. That's not the point. The point is that mixtures of clean compounds are not dirty mixtures. When you know what you have in a mixture, it's a good mixture. You know what is there. So a mixture of instructed components is what you are up for here. And you have a sort of a constitutional diversity which is instructed. Sorry, where is it? Yeah, that's correct. Now the last point, which was in fact the paper in which at the end of it with Bernie Hasenknopf he introduced this idea of dynamic chemistry, is this one. This we have seen, and we know it gives the pentagon. You know, we have seen that. We also know that when we change the anion, you get a hexagon. So what does that mean? That means that this system can generate either a pentagon or a hexagon, depending on what is around, which then makes you think that, in fact, from the building block and from a certain number of metal ions, you can generate square, pentagon, hexagon, something else, whatever. Of course, we have only 2 examples, but it's enough to take the next step, which is to say these dynamic features make it possible to look for a chemistry where what you get depends on what is around. When chloride is present, you get a pentagon. When sulfate is present, you get a hexagon. So it's a system which is combinatorial, but in a dynamic fashion. And this then led to the realization, which is something one should have seen much earlier. Everybody knew that supramolecular entities are dynamic. The molecules are held together in not too strong way so that they can fall apart and reassociate. This was taken for obvious to all of us. But then the question is to realize, can we do something with it? Is that interesting? Is there something special to this possibility to dissociate and reassociate? So you can call that, so supramolecular chemistry is a dynamic chemistry. It's a dynamic non-covalent chemistry. Then comes again a step which is again sort of taking a turn 180 degrees from what one usually does. Can you extend that to molecules? In other words, make dynamic covalent chemistry. Make molecules which break apart, which fall apart. This is something we all, at least, are trained not to do. You don't want to make molecules which are unstable, usually, when you synthesize something. But what happens if you make the molecules unstable? If you introduce reversible covalent bonds, then the molecule can dissociate, reform, or maybe exchange its components. And that is a dynamic covalent chemistry. Putting both things under the same heading leads to the idea of a constitutional dynamic chemistry, which then makes possible adaptation by variation of a constitution. Now this area has developed a lot in recent years. Dynamic covalent chemistry, the supramolecular is our work. The dynamic covalent has been developed here, also very well by, at the same time more or less, by Jeremy Sanders in Cambridge, and you will hear something more from Schaefer Otto when he will be here. So I would like to insist on the fact that this dynamic chemistry is very different from what is, let's say, the classical approach. Reactional dynamics, that is dynamic chemistry in all chemical physics books. Motional dynamics is very important, and many people have realized that molecules which move, like in biology, are very interesting for making motors. And here one can cite Jean-Pierre Sauvage's group here, Fraser Stoddart, David Lee, and of course also the Bologna group, where you try to make molecules which can be looking sometimes and calls it machines. A machine does a work, but so they're not really machines. But they move, they do things, they have motions. This is very important, very interesting. And Feringa, I forgot. This is a dynamic chemistry which deals with the constitution of the object. It's not a reaction, it's not motion, it's constitutional. It makes the constitution of the chemical entity dynamic. Let's see what one can do with this. What is it good for if you look at this area? First of all, of course, it generates diversity. You get a mixture, a mess, so to say. But then you can do selection. So on one hand, molecular recognition processes, maybe we can do that. How would that do? We'll see that. One could have constitutional dynamic nanostructures and constitutional materials, dynamic materials. What about biologically active substances? Let me simplify here the approach, simply because it's quicker. Lock and key, Emil Fischer. If you are a medicinal chemist at a big company, you want to have an action, you act on some kind of a biological target, you would like to make the right key for that target. That means the right molecule which binds there, only there, and does what it should do. Now this means that you have to know the structure of that target molecule. You have to be able to design the key, and then it has to bind. So that takes a long time, because in many cases you don't know what the target looks like. You don't have the crystal structure of the target molecule. So came up the idea. In fact, the first paper was by Hungarian Arpad Furka, which is forgotten a bit, but he was I was at a meeting I think it was in Budapest many years ago, and that paper I noted, he had made dynamic libraries of peptides, Arpad Furka, long time ago. Of course, then other people have picked it up, but he's the first one. So, make many keys, combinatorial chemistry. The approach is the following. Let's count on chance. We make 100,000 of those things. We have high throughput screening. We have fast robotics. We test all these things. Now companies do that. And we can test 10,000 molecules in a day, maybe more. Many different keys. You try them all, and you have a bit of luck. You get something which fits. If the first 10,000 don't work, you make another 10,000, another 10,000, until you find something. But that is not very interesting in terms of understanding. So the combination of the two may be interesting. You can try a combinatorial chemistry, but which is dynamic. What does it mean? You want to use the power of combinatorics, generating many, many, many things, with the power of recognition, which is the right key. How do you do that? These are components of different shapes and different colors with black dots. The black dots are functional groups which can reversibly connect and disconnect, connect and disconnect. So when you mix those together, you get a mess. You get a lot of interconverting entities with different combinations. The important thing is not that they are present, but the fact that they are accessible. Out of this set of components, you can make a very large set, in principle, of constituents which reside in all the possible combinations of these. So you have diversity generation, and you have a reversible set. Okay, at that stage, then you have to ask something. You have to take your telephone and call up Monsieur Le Chatelier, the law of mass action. The law of mass action tells you that the best thing in here, if you add something which binds, it will select the one which binds best. If you add a receptor to that, so this is combinatorics. Now comes in information and recognition, and if this is the receptor, it will, out of this mixture, pick up the pieces which make the best binder, which means the lock assembles its key. You don't have to do it anymore. It does it for you. Now, that looks good on the paper. In principle, it is correct, point. But it's quite clear that if you have here, let's say 10,000 different entities, each of them has a very low concentration. So you must have a binding constant which is high enough to pick up that concentration. But that also means, so that's the bad side of the coin. But the good side is that if something is seen, then it means that that is very strongly binding. So if a bad side, it means that we need strong binding, otherwise you don't see anything. But if you see something, you have a very good compound for binding. So the log assembles its key, and this can be used for drug discovery, enzyme inhibitions, and so on. Let me now give you just, I have two examples, maybe restricted to, okay. Among the reversible reactions of organic chemistry, in fact, it's an interesting field now. Let's make organic reactions reversible. Of course, in principle, the principle of the fact of micro-reversibility is that any reaction can go back. But of course, if they are like this, the chances to go back are very small. So you have to try to find reactions which can be reversed or controlled in given conditions. And this is something, an interesting field also. An evident and simple one is the condensation of an amine with a carbonyl. It gives an amine, it is reversible, everything is happy, that's good. Furthermore, if you take away the water, you block it, it cannot go back. In other words, it's an interesting reaction, first of all, because it's very general, it works very well known, and you can control the reversibility by having or not having the water. Another system is disulfides, that's what Jeremy Sanders mostly used. By disulfides, you have only SS, you cannot distinguish the left from the right. Here you distinguish the amine from the carbonyl. This is A, that is B, and you know which is A, you know which is B. And this is acyl hydrogens. All right, so you can generate dynamic libraries based on CN double bonds. So the first case which was studied, this was Ivan Huck at that time. After having started this thing, we said, okay, let's apply it, let's test it, the principle, on an enzyme, carbonic anhydrase. This enzyme interconverts CO2 water with carbonic acid, and it is a very important enzyme, especially in the lungs, because that's what does the interconversion. And it has an active site which people have tried to make inhibitors for. And one inhibitor, a very good one, with 1 nanomolar, stability constant 10 to the 9, is this very simple molecule. It has here, there's an active site with a zinc, and an active site with a hydrophobic wall. So this unit is a sulfonamide group, which binds to the active site zinc. And this is a hydrophobic entity, which binds to the hydrophobic wall, benzylamine. So what can we do? Let's start simple. 4 amines, 3 aldehydes. One of the amines is benzylamine. We know that that is part of the final compound. And one of the aldehydes is this aldehyde, which has a sulfonamide group on a benzene ring, benzene sulfonamide. Now, of course, we know that the condensation of an amine and an aldehyde giving an imine is not the same as the amide here. But maybe, if this is dominant and if this is dominant, maybe one can do it, and one can use that. So, here we have 4 times 3, that's 12. One of these 12, this here, is a combination which is very close to the best inhibitor. So if you start with a mixture containing all the 12, and if you add the enzyme, you should amplify this one, because it is closest to the good binder. That's indeed what happens. If we just compare 2 among the mixture of 12, this one, which is the one we are looking for, the one which should be the best, and this one, which has the same component sulfonamide, but another component here. No carbonic anhydrase. They have about the same amount in the mixture with carbonic anhydrase. This is strongly amplified with respect to this one, showing that indeed the interaction of this dynamic library with the enzyme selectively amplifies this compound, which is the best, which is closest to the best inhibitor. I guess I will drop this example. It's a bit more, just to show you, this is 690 constituents. That gets more complicated. Then you have to develop a method which one can call dynamic deconvolution. Let me just say, this is, no, I should just say a word. Concanavalin A is a lectin, that means a protein which binds sugars. It is a tetramer, but the important thing is this, it binds 3 mannoses, trimannoside, mannose, mannose, mannose. So you make 6 different sugars, one of them is mannose, that guy, and you take units which can bring them together by condensation of this aldehyde which has been introduced to this NH2. This now gives 690 constituents. Now you have a problem. How do you find out which is the good one? So you do the following. You do mixed type libraries. You take one component out, and everything rearranges and generates all the constituents except, of course, the ones which contain that component. If what you take out is important, there's something, you will see it. If what you take out is not important, you will not see it. So this is the blank. That's a complete library, which means there's something binding in there, something binding strongly, because this has completely been repressed. You take out 1, 2, 6, big signal. And the other ones, J, G, and I. What are they? Mannose 3. So that doesn't mean that in this way you have found the best binder, but you already know at this stage. Suppose you know nothing about concanavalin except that it binds sugars. This tells you that it wants to bind mannose and it wants to bind 3 of them. And then you can continue studying what's going on. Okay, now something about materials. That's at first sight you say, do you really want to make dynamic materials? Because dynamic materials means materials which are not stable, which can fall apart, which looks like a stupid idea. In principle, just to set the picture, these materials can be molecular dynamic covalent, thanks to reversible reactions, or supramolecular non-covalent interactions. And this, if you apply that to a typical material, a polymer, that means making dynamic polymers, which we like to call dynamers, dynamic polymers. And they can also be biomaterials. The formation of supramolecular non-covalent dynamers rests on polyassociation by non-covalent interactions. And the polycondensation, this polyassociation, polycondensation through covalent reactions gives you molecular covalent dynamers, where the connecting groups, this is one monomer, that's the other monomer, the connection between the yellow and the red points can be either recognition when it is non-covalent, or a reversible reaction like an amine and a carbonyl when it is covalent. These materials have interesting properties: self-healing, responsive, adaptive. In fact, I will show you a very short movie about the self-healing one in a moment. So you can play the games polymer chemists play usually. You have the building blocks. You can get linear polymerization, either supramolecular type by polyassociation or covalent type by polycondensation. And you can do cross-linking and capping and all that. So the first case, we introduced that in 1990. The reason why I say that, you will see in a moment, there's something quite interesting coming out. The first paper on supramolecular polymers was this paper in 1990. This was done with components which were for industry totally without interest, too complicated, but it showed the principle. This is a recognition group having donor, acceptor, donor of hydrogen bond units. This recognition group of another component is acceptor, donor, acceptor. So this monomer with 2 recognition groups, one at each end, is complementary to this monomer with recognition groups at each end, this complementary to that. In the middle, there is tartaric acid as a spacer. And the R here is a chain C12H25. Why do I say that? You will see. So you mix this, and you get this, which is linked where the units, the monomers, the molecular monomers, are linked by supramolecular interactions to generate a supramolecular main chain polymer. To show that this is not just anything, it has interest in itself. That's a solid. That's a solid. That's a liquid crystal with a very wide range of liquid crystallinity. Then we wanted to know more about, and we found out that they make fibers, nice fibers, and so on. We should have pursued that a bit more, looking more deeply into the fibers. But anyway, this is what was demonstrated. By looking at X-ray scattering with the group of Madame Levelu in Orsay, it was found that in fact it's a triple helix. These main chains make a triple helix along a cylinder, and the C12H25 side chains stick out. They stick out, and as you increase the concentration when you make it, it's quite obvious, supramolecular polymers, because there is an interaction which is a stability constant, depend on concentration. When you have low concentration, you have a nucleus. Larger concentration, they grow into a filament. Even larger, you get a tree. And even larger, you get these very thick fibers. Why? Because, pardon, where is it? These side chains can entangle, and then these cylinders stick together. So that is one question one may ask. Sequential assembly. That's a case of sequential assembly. These are the molecular components. You get a supramolecular main chain polymer. These then form a triple helix, and these then by the side chains can entangle and form the fibers here. So that's a sort of a conditional assembly. First you have to form the chain, then you form the triple helical strand, and then you form bilateral association the fibers. This is just to forget that. Now, this is a case where I think sometimes we should feel happy that we must do basic research, even if we don't know what the applications are. This thing we did in 1990, this first paper, 1990. And it was developed by a number of people then, Supramolecular Chemistry. Bert Meyer has done fantastic work in Eindhoven, and a lot of people around the world have done work on supramolecular polymers. In October 2013, about a year ago, I got an email from the CEO of a small company saying, look, we have used supramolecular polymers for making biomaterials. I said, oh, come, what did you do with it? What they did, they were able, of course it requires work, on the principle of supramolecular polymers, because they are reversible, to make a material which can be used for cardiovascular implants. And this was applied to children which have a severe congenital cardiac malformation. You will see why children is, we'll see that, I can say it right now. Why children? Because if you have a biomaterial implanted in children, it's invaded very quickly by cells which grow. So you can use that as a framework, as a sort of a prothesis, if you want, which is invaded by the normal cells. So this company is Xeltis. It's based in Zurich and has a lab in Eindhoven. You can make, they have made special polymers. They have a special technique to make it. It's not all that simple, you know, you don't find it over the weekend. They are biodegradable, and they are processed so as to have an environment for regeneration of native tissues. And then next step, you have to find somebody who's ready to implant it. First in man, this person, Leo Bokeria, never heard of him before. I know him now, he's quite a guy. At the Bakulev Center for Cardiovascular Surgery in Moscow. I learned also, that's a very famous center for pediatric surgery. And here is Dominika. She was implanted in the October 2013. Now it's a year, she jumps around, she's normal. It has been done now with 5 other, maybe more. This is the last information I got, with 5 children altogether. And it works. Now, one can also reflect here, and when there are politicians in the room, I like to say that. What is the way where you get from the idea of supramolecular polymers to cardiac implants in children? No way to predict. First, you have to have the idea, you have to make the polymers, and so on and so on. Then somebody has to notice, and then many people have to develop it. Some fellow has to notice, or lady, has to notice that one can do something with it, which is a biomaterial. Then you have to make the right one. You have to find a technique to make the right biomaterial to handle it. For that, you have to find the money, because you want to create a company. Then you have to find the surgeon who is ready to do it. Look, how can you predict that? So I think let's do our work, and there are clever people around, not just us in this room, who will be able to exploit it if it is interesting. And I'm sure there are many other properties which can be developed from this fact that supramolecular materials have properties which other materials don't have. Now, let's go to covalent dynamers, where again it's dynamic, but where the dynamicity results from a reversible covalent bond, either polyimines, polyacyl hydrozones, and so on. Now, the acyl hydrozone group is especially interesting. I don't want to insist much on it, but just to make a remark that the hydrazid condensed with the carbonyl gives an acyl hydrozone, acylated hydrozone, where this is an amide, like in nylon, and this is an imine. So this gives reversibility, and this gives the hydrogen bonding, like in nylon. So you can make dynamic nylons and things like that. We have developed a lot of this work together with Mitsui Chemicals. People from co-workers from Mitsui Chemicals in Japan came to my group. They developed the basics, and then they tried to apply it there. I will not tell you much about that, but I want just to show you what it's good for. So as I said, this is like a peptide bond, so you can think of dynamic proteins, and this is a dynamic polyamide. You can think of dynamic nylon and things like that. This is what Mitsui Chemicals made, sort of green plastics, where it's a very nice material, in fact, they made here, which you can then check. I hadn't time to put it, I didn't want to put it in, but you put it in water, it disaggregates slowly. And the rate at which it disaggregates depends on how you have made it, what are the components. So you can regulate, you can make dynamic polymers which have a controllable time for degradation in water, in the environment. Now, suppose you have a combinatorial library of components to make these dynamers. If you apply a stimulation to this, the stimulation in principle should force a rearrangement of the whole thing to generate a dynamer which is good for responding to stimulation A, or responding to stimulation B, or to C. What can one do? Suppose you have 2 films. One film is AB, AB, AB. This is one polymer. The connections between A and B is a dynamic connection. Then you make a film A prime, B prime, A prime, B prime. Now you superimpose the two. What you can hope for is that because this bond can break, you can now connect B prime with A and B with A prime. In that way, you generate the 2 combinations which are not present at the beginning. At the beginning, you have AB and A prime, B prime. So you can generate B A prime and B prime A. Okay? What is this good for? Can you modify the mechanical properties of your dynamers? This is a polymer of dimethylsiloxane units. Dimethylsiloxane is a very floppy type of stuff. You have NH2, you have aldehyde, you mix, and you get this soft and stretchy, very soft and stretchy film, a terrible film. In terms of mechanical properties, horrible. Nobody knows Nobody would be interested in looking at something like that. But we wanted to start with this, because if you now treat this thing, you make that, which you just saw, and you now add to this what you might call hard monomers. This monomer with a hard center, so hard meaning not so flexible, and this monomer with still flexible, but not by far not as flexible as dimethylsiloxane containing units. You add it, 25%, the film looks good. Not good, looks better. 50%, now it is rigid enough not to bend down anymore. 75%, you keep flexibility, but it's stronger. And you can measure the mechanical coefficients of that, and indeed, you can progressively transform a soft and stretchy film into a tough film. What about optical properties? I'm going a bit fast here, but I think you are waiting for something out there. So what about optical properties? Film AB, film A prime, B prime. AB is transparent. A prime, B prime may be a little bit colored, a little bit fluorescent. Then you superimpose. According to what I said, at the place where you superimpose, you can now connect A with B prime and B with A prime, making the two new combinations which don't exist at the beginning. One of them may have color or fluorescence. And then you will, of course, see it. So my Japanese co-workers, Japanese like very these nice pictures. They make this cat. The head and the ears is one polymer. The mustache, the eyes, and the inside of the ears is the other polymer. You put them on top of each other. You heat. There would be strong heating, but they wanted the result quickly. Color, fluorescence. So it only has color and has only fluorescence where it is superimposed, which means that indeed you have generated one of those two, and we knew which it is because we did it, of course, separately. It has color and has fluorescence. Now, self-healing polymers. We wanted to have a Diels-Alder reaction because the Diels-Alder has an advantage. You see, when you make imines, you get water. Now, this is interesting. If you remove the water, you stop it. But when you have water present and you lose something. Now, Diels-Alder is a good thing. Everything that is in the starting materials is present in the product. So if it is reversible, it can be reversible all the time. There's never something else formed. So we were looking for a room temperature reversible Diels-Alder reaction. After a long search, we found this one, which is sort of a strange thing. Dimethylfulvenes, fulvenes with cyanoethylenes give something which is Diels-Alder reversible at 25 degrees, perfectly reversible. This means that if you make now a monomer with two cyanoethylenes and another one with two fulvenes, you mix them, you get a polymer where the connections are all the time fully reversible. So you make a film out of it, you cut the film, you press it with your fingers, and you can pull. And it sticks. So it's self-healing. This I don't want to get into, but, sorry. I think I have something. That is one we made, a self-healing polymer. Let's have a look at it. This was done by Nabarun Roy, an Indian postdoc. Just press with your finger, not more. It sticks pretty well, huh? And the resistance is almost the same as before. You lose 10% about in ability to. Okay, that's it. Now to get back to the other thing. I drop this. I drop the bioanalogues. This is too long. And I would just like to say a few words on this, because that is the present step which we are especially interested in. Adaptation. Dynamic polymers can respond to environment, not just dynamic polymers, but dynamic entities, to phase change, to physical effector, chemical effector, and so on. And this can build networks. Now, there's too much here. I will quit this. Let me just quit this. Okay, this I should use. It's a bit complicated, but I think it illustrates well what's going on. This is a carbazole hydrophobic core with 2 aldehydes. That's the same with 2 ethyl hydrogens, NH2 groups. Here is a hydrophilic side chain, hexaglyme. So this thing is soluble in water thanks to that side chain. This doesn't want water, but the other one makes it soluble. So you can make big ones, carbazoles, similar units with small, just phenyl rings. So this is carbazole, carbazole, phenyl, phenyl, carbonyl, carbonyl, NH2, NH2. First thing you check what is going on. You mix this one, the carbazole, with this one, this carbazole. You get a polymer which, by the normal techniques which polymer physicists are using, can be shown to be a rigid rod by small angle neutron scattering, thanks to the work of Eric Bühler in Paris, with whom we collaborate on that. The molecular weight has been determined, and so on. Now, that is not so interesting. That's just sort of trivial. It's just you connect those things. But the fact that it works makes you ask a question, which is the following. Suppose we take the carbazole aldehyde, dialdehyde, and we put it in presence of the phenyl bis-hydrazide and the carbazole bis-hydrazide in water, because all that is soluble in water. Now the system has to make a choice. This aldehyde, will it polymerize with this or with that? Hydrophobic effects would tell you you want to remove from water everything that is very hydrophobic. And if you make a rod with the hexaglyme sticking out, the center is hydrophobic. So you want to eliminate in principle, which means that this mixture should selectively polymerize these two and leave this out, which is exactly what happens. You get the same polymer as the one I showed before, and this one sticks in solution. That's very easy to see by NMR. You realize that this thing, it's an infinite width. The signal is completely flat, and this is sharp. So you just have to integrate, and you see how much you have of that. But then you can do another experiment. If what I tell you about hydrophobic effects is correct, if you go from water to organo-water solutions, you should lose the selectivity. And indeed, so this is, if you add acetonitrile to the water, you lose the selectivity. And at about 80% acetonitrile, you have statistical polymerization of this with that, of this with this and with this. So you have chains where both things are included. Now, this type of reversible systems can be considered as forming a network. And this is what I would like to finish with. It will not be very long. Suppose you have AA prime and BB prime. AA prime, same functional group, for instance, 2 aldehydes. BB prime, 2 amines. They can combine as you realize, to form 4 constituents: AB, AB prime, A prime B, A prime B prime. Now these form a network, a two-dimensional network, where you can use a square to represent it with AB, AB prime, A prime B prime, A prime B on the corners. These are related by connections, relationships, where on the edges you have components which we have constituents which share a component. AB shares A with AB prime and shares B with A prime B. These are antagonists. They work one against. If AB increases, the other ones will decrease. However, AB on the diagonals with A prime B prime, they have no common component. A prime B and AB prime have no common component. These are agonists. If this changes in one way, that will change in the same way. Now we can see that. They can be modulated by physical properties or chemical effectors, and they are adaptive. How? Let's have a look. Now this is the last example, I think. A bit complicated, but it illustrates very well what's going on. It was also done by Shunsuke Fuchi from Mitsui Chemicals. Okay, the monomers we used here had the following composition. They had a center part, which was either a donor, dihydroxynaphthalene, or an acceptor, this bis imide, and a cation binder chain. To these things were attached an aldehyde or an amine, so as to be able to make a reversible bond. So if you combine those things, you get these 4 monomers, the diamine with the donor in the middle, the diamine with the silicon. We use that also because that's the dead one, the one which doesn't do anything, which shouldn't do anything. This is the dialdehyde with the acceptor, and that's the dead dialdehyde with, again, the silicon. Out of these 4, you can make 4 polymers. P1, M2, M3, M2, M3, that's the one which contains the acceptor. P2 contains the donor. The other ones are the dead unit, the silicons. P3 has the acceptor, the donor, and the acceptor in the chain polymer. And P4 is dead, silicon, silicons. That shouldn't do anything. So, what will happen? Of course, you could sort of think, all right, donor, acceptor in the same chain, this is the one which is probably preferred. Now we were lucky, and the reason, now I should also add one thing, the reason why we also consider that chain, which is seen here, you see this is the chain here, because we can now bind cations. Now it gets a bit complicated, but you will see in a moment what it is. First thing, we had a lot of luck there. We made a trimer having donor, acceptor, donor, with here units NOO, OON, which can bind a cation. And indeed, when this substance is treated with sodium triflate, you get a very nicely sort of a start of a helix, if you wish, this way, where sodium binds to these sites here and wraps, and the ligand wraps around the sodium ion, giving this unit here superposition of donor, acceptor, donor, stabilized by the binding of sodium in these loops here and here, the folded trimer. Now, with this in hand, you can say that if you make it now a dynamer, a polymer, this polymer should have these features along the polymer with sodium. And this agrees with the NOESY spectra, or the spectra which have been done. The molecular weight is about 45,000. And so this is what you should have. Now, the interaction between the donor and the acceptor also gives a color. So This is the unit in absence of any metal ion. With lithium, sodium, you get a rather strong color. Potassium less, rubidium less, and cesium close to no metal. Now this is understandable because as the metal ion gets bigger, the donor acceptor go farther apart. And so the charge transfer is less strong. Now that is one thing. This was just interesting in terms of optical properties. But in terms of the dynamics, the responsive property to the addition of the metal ion. Let's see. Let's look simply at the case of no metal and the case of addition of sodium. Okay, so that's polymer P1. The P3 is the one which has both donor acceptor. Okay, you start, this is P1, P2, P3, P4, and you will only look at the case of sodium. In presence of sodium, that's in absence of anything. In presence of, wait a minute, in absence of any metal ion, this is the amount of P1 you have, about 22%. That's the amount of P2. You can see that in an NMR spectrum by looking at the imine signal. That's the amount of P3. That's the amount of P4. They're not too different. Okay, they're not identical. That is 22%. That is about 27.5%. But they're more or less statistical. Not exactly, because you would expect P3 to like to be, it's the donor acceptor unit. So that one is a bit preferred because of interactions. But now, if you add sodium, you should favor that form. And indeed, you now add the sodium cation, and the response is the following. The one, when you add sodium, P1 decreases from 22 to 7%. Same thing for P2. P3, strong increase. And P4, also strong increase. Now that shows everything I told you earlier. P1, P2 are antagonists to P3. Okay? P3, when you favor it, it diminishes P1, P2. But because P4 has components which are not present in P3, it can also increase. Okay? These two are antagonists to P3. P4 is the agonist to P3. So the agonist, the fact that you force P3 to form because of sodium, forces also the agonist to form. Now, this is only indicating that you have added sodium. That doesn't mean that sodium binds to P4, of course. Now, let's reflect just a quick moment on that. Statistical distribution more or less at the beginning, 22, 22, 27, 27. Effect of sodium, P1, P2, bluff, this goes up and this goes up. And forced distribution by sodium. So the component distribution is driven by sodium. This is the square at the beginning, more or less statistical. You add sodium, this is now very big. And because this is very big, this must also be very big. That's an adaptation to the addition of sodium. So it's an adaptation driven by sodium plus, the effector you have added. What is very interesting in terms, if you think about it, the amplification of the agonist. In other words, you do something which amplifies P3. As a consequence, P4 goes up. P4 doesn't do anything with sodium. But because sodium forces P3 to go up, P4 must form. In other words, the fittest for sodium drives the production of the unfittest for sodium. This is very interesting. Now suppose we have a case, but I don't think I have it, and I wouldn't show it anyway. If the unfittest, for instance, has a color or fluorescence, but you cannot make it directly. So you just drive the fittest, and the other one, color, will obtain the color, because this one has to increase also. It's like in evolutionary biology, it's quite interesting. Huh? The fittest, for instance, if animals live on ground and in the sea, they're separated, and if one eats one thing, the other eats, and which the other one does not eat, the other one has everything to eat. so it can grow. Okay, so I think this is probably the most important thing here, that the agonist relationship makes you able to influence what's going on somewhere else and to increase it or to decrease. It's also an influence. And in fact, I think these networks are very interesting because it's also a way, I have not put that slide in, but I watched just a few words. It's also a way to transfer, first, to store information into a constitutional distribution. A given distribution tells you what you have added. For instance, if you add not sodium but potassium or rubidium or cesium, from what comes out, you know that which one you have added. If somebody didn't know what you have added, but just looks at the distribution, you know what has been added. You can do reverse engineering, because the distribution will tell you. That's number one. Number two is also that you act at a point where you have never been. By acting on P3, you do something to P4, you have never been there. And I usually compare that. Look at the airline network in the USA, for instance. You have a company coming in and say, I want a flight from Boston to Chicago. Okay? So the people say, all right, well, okay, you have your flight slot. But now when that plane lands in Chicago, the people in Chicago have to rearrange their schedules. So the planes which go from Chicago to San Francisco will be influenced by the plane which goes from Boston to Chicago. And the guy from Boston has never been in San Francisco. So in fact, through these networks, you rearrange, you affect things where you never go. You transmit a signal without being there, without messenger, so to say, simply because you act on the distributions. And I think this is something very interesting, which of course one has to do with more complicated things than just 4, but at least the principle is there. So we conclude, that is what I talked about, that this dynamic chemistry allows adaptation and maybe generating adaptive systems, materials, and technologies. Because your system can change its constitution, and I insist on the fact that it's not just an adaptation of a shape, it's an adaptation of the intimate constitution of the object. You act on the object itself, not just on how it looks, bend, helix, or whatever. So, molecular chemistry at the start, you can't do anything without molecular chemistry, it's quite obvious. You can construct supramolecular chemistry on molecular chemistry and design the objects. Then realize that these things can be made dynamic. You can develop a constitutional dynamic chemistry. Then selection can operate because you have these dynamics, and you can try to develop what you may call an adaptive chemistry, and maybe later on evolutive chemistry, where what you gain in the first step is kept to do the second and kept to do the third, and so on. So that's more or less where we stand right now. There are many other things I could have told you, but I wanted to give you sort of an overview of how things evolve. And this is certainly the thing which we are now quite excited about, the fact that one can make systems which are adaptive. And also this question of acting where you never go, doing something through intermediates. Okay, have a good week.